So, all right. So this is 5.7, change of variables in multiple intervals. We have a couple of slides of notes first. Sorry. So if you are one of my note takers, you can see the learning objectives are on here. So we have a nice definition. And obviously when I do the download, you'll be able to see the paragraph, but also if you follow along in your book at all, it's in your textbook as well. I just like to pull in some stuff that I think is important for you guys. You can see that we're definitely going to have a little bit quicker of a class. We're only covering 5.7. It's the last section in chapter 5. And then we will do your review on Thursday. Okay. All right, so for some of these, it was just easier to copy over the whole solution, but we do have some stuff that we should talk about. So in order to show that T is a one-to-one transformation, we have to assume that T R sub 1 theta sub 1, so T R sub 1 theta sub 1 is equal to T R sub 2 theta sub 2. And as shown, and shows a consequence that, so then R sub 1 theta sub 1 will have to equal R sub 2 theta sub 2. So if that's the case, we would have where we started at up here. So we write it over here. And I have x sub 1, y sub 1 equal to x sub 2, y sub 2, which would lead us to also have r sub 1 cosines 1 and you guys can probably figure out the pattern as I'm writing it, so you can write it down to okay, so all of that comes from that primary premise. So if we divide we would do we divide here, then we would get cosine theta 1 over sine theta 1 equals cosine theta 2 over sine theta 2, which is the cotangent of 1, cotangent 2, which just means that. All right, since the cotangent function is a one-to-one in the interval, that interval was given to us as okay. And also, since R is between 0 and 1, then we would have, it's not really, okay, so then we would have R sub 1 equal to R sub 2, and theta sub 1 equal to theta sub 2. So that means that we have this part, and that the T is a 1-to-1 transformation for G into R. So then to find T inverse x of y, we would solve for R theta in terms of xy. Just wondering why they gave us so much. And then go, here's the solution too. Crazy. So okay, so then we know that R squared equals x squared plus y squared. And then you know that tangent theta equals y over x. So then this portion would be R equals square root x squared plus y squared. And then theta equals tangent inverse y over x. All right. A whole bunch of stuff for you to work through on that problem. Right? Okay. All right, so let the transformation T be defined by T UV equal XY, where X equals U squared minus V squared and Y equals UV. Find the image of the triangle in the UV plane with the following vertices. So that's probably what this is. So for side A, not SID A, U is equal to 0. So then V falls between 0 and 1, transforms to x equal to negative v squared and y equal to 0. So this is the side where A prime joins 1, 0, and 0, 1. Sorry, that's a negative 1. So for the B side, And that transforms x equal to 0, y equal to u squared. So then B prime joins so then that transforms so from that you can take away so then C prime makes the upper half of the parabolic arc. Okay. All the points in the entire region of the triangle in the UV plane are mapped inside the parabolic region of the XY plane. So that is the background information for the solution that they gave you. All right, we have a couple of slides of notes. And I apologize if you have a hard time reading them at the moment. You can always zoom in on the PDF, or again, they are in your textbook. Okay. All right, so clearly we're going to use the Jacobian. Should be something from your earlier calc experiences that you should have heard. I feel like I remember it more from linear algebra than I do from calculus. But that's probably because I enjoyed linear algebra so much more than calculus. Okay, find the Jacobian of the transformation given example 5.65. Oh, that was, okay, so, okay. All right, so the transformation in the example is T R theta equals R cosine theta R sine theta, where x equals R cosine theta and y equals R sine theta. So the Jacobian is That's going to do something to us at some point. I don't know what. There. Nope. Trash. I hate when this does this to me. Whatever. Hopefully we'll be able to work around it. Oopsie. No, guess not. I love this tablet, but I swear sometimes it just does things that I don't understand why. But that is not a 2. So that just leaves us with 4. Okay. All right. All right. So this one is slide 8, and it's going back to okay. All right. So we're probably like I think we're like almost halfway done. All right, so the transformation in this example, remember, was the T U V, and then we had U squared minus V squared, and then U V, where X was equal to U squared minus V squared, and Y was equal to U V. Okay, so we're gonna find the Jacobian again. So J U V. That is a V. Oh, that gives us an answer of 2U squared plus 2V squared. Alrighty. So hopefully the Jacobians you guys will feel comfortable with on the homework and the exam. It'll definitely be on the exam. So we have another little page of notes. Sorry. I think we have like maybe two more nice ones and then some of them get kind of long. All right. Okay. All right, so it says changing variables from rectangular to polar coordinates, consider the integral, and then use the change of variables and the resulting integral. So it does give you the answer there. Squaring and collecting the terms, we would find the region is the upper half of a circle. So you would have x squared plus y squared minus 2x is equal to 0, which is y squared plus x minus 1 squared is equal to 1. So in polar coordinates, the circle is r squared, or r, sorry, 2 cosine theta. So the region of integration in the polar coordinates is bounded by okay. So then now we have to find the Jacobian. So we know then that J r theta equals r, and that was from example 5.67. Since r is greater than or equal to 0, we have the absolute value of the Jacobian as r. The integrand of square root of x squared plus y squared changes to r in polar coordinates. So the double integral. So we did all of that to set up this double integral becoming 0 to pi over 2, 0 to 2 cosine theta, and then r dr d theta. So then that's just 0 pi over 2, 0 to 2 cosine theta r squared dr d theta. And that's it. That's all they want. They just want that answer. All right, so the next problem is a bit longer. So we may need to add a slide, I'm not sure. Well, if this is all the room I left for myself, then yeah, we'll have to leave a slide or get a slide. All right, so it says consider the integral. You can see it where r is the parallelogram joining the points 1, 2, 3, 4, 4, 3, and 6, 5. So the following figure. Make the appropriate changes of variables and write the resulting integral. So notice it's not telling you that you have to solve it. You just have to write the integral. Okay. So first we need to understand the region over which we are going to integrate. The sides of the parallelogram are and they actually give them to you right there. Yes, these are all the sides. So clearly the parallelogram is bounded by the lines, those 4 lines. You can write them a little bit differently, but that's basically the answer there. So notice if you were to make u, so if we were to do a u substitution, we were to make u equal to x minus y and v equal to x minus 3y, then the limits of the integral would be -1 to 1 and -9 to -5. To solve x and y, we first multiply the first equation by 3 and subtract the second equation. So, show you that. So we multiply the first by 3 and subtract the second. So 3u minus v equals 3x minus 3y minus x minus 3y. So that'll give us a 2x. Then we would have x is equal to 3u minus v over 2. And then if we simply subtract the second equation from the first, you would get oops. Okay, let's add a slide. All right, so thus we can choose the transformation. So du v is going to be 3 minus 3u minus v over 2, comma, u minus v over 2. And then we need to compute the Jacobian. So okay, so then the absolute value of that would be just 1/2. Also the original integrand becomes So therefore, by the use of the transformation t, the integral changes to so that's a lot easier to compute. And it is going to end up being 0. So it's just one example of why we transform integrals. Okay. All right. I forgot that I added a slide. Hopefully we won't have to add any more slides. We will be good to go. Okay. All right, so problem solving strategy, change of variables. So the first thing you want to do, which I think I've said this from nearly day one, is you want to sketch the region given the problem in the XY plane and write the equation of the curves that form the boundary. The second step is, depending upon the region or the integrand, choose the transformation, either x equal to g uv or y equal to h uv. Determine the new limits of the integration in the uv plane. Find the Jacobian. In the integrand, replace the variables to obtain the new integrand, and then replace dy dx or dx dy, whichever occurs, by the Jacobian, and then du dv. Okay, so you follow those steps each time, and you're going to end up with the right answer. As long as you do your more simple. Okay, so we will look at this problem next. Try to make that big enough for you. Yeah. So it says, using the change of variables u equal to x minus y and v equal to x plus y, evaluate the integral, where R is the region bounded by the lines and the curves, and then you can see the figure. So, how terrible would it be if I just let you guys think that that was the only solution? All right, so given that we're talking about this part, all right, then we could solve for x and we would get u plus v over 2, and y is going to be v minus u over 3. Nope, 2, sorry. Should have known it was 2. And hence, the transformation we would want to use would be, so because of this, what's going on? What just happened? So that is going to be okay. So then the lines x plus y equals 1 is going to become v equals 1, and x plus y equals 3 is going to become v equals 3. The curves x squared minus y squared equals 1 is going to become uv equals 1, and x squared okay. So we can describe the region S as oops. Okay. So then the Jacobian, are you guys, I'm assuming at this point I don't have to keep writing out how to find it. I'm just gonna kind of skip the middle section. So you guys may certainly write it if you need it, but I'm gonna try to save us a little bit of space. Okay. So then the transformation, the integral Okay, so if we do the evaluation, then we end up with 1/2 Okay. And just so you guys know, as a side note, on your test, some of the answers they wanted, like, kind of like using, square roots, like they wanted you to keep the radical. If you gave it as a decimal, I just made sure it was equivalent, and I gave you the credit for it. Okay, here we have what is presumably our last page of notes. Okay. Again, make sure that you're going to go over this in the PDF part or the textbook to make sure you get all the important parts. Okay. I can't remember if we're supposed to look at the image first or second, so I'll just go ahead and give it to you now. Okay, so the question here says, and this is just for part A, derive the formula in triple integrals for a cylindrical, and then in spherical coordinates. So for cylindrical coordinates, the transformation would be P r theta z equal to x, y, z from the Cartesian r theta z plane to the Cartesian x, y, z plane. And you can see the figure. So that would tell us that x is equal to r cosine theta, y is equal to r sine theta, and z is equal to z. So then the Jacobian, and you saw it, the slide before, it's very similar to what we were working with. I will do my best to squeeze it fully in here for you so you have it at least once. Oops. Hopefully you guys can read chicken scratch on all of this. So then for this problem, that would be cosine theta, sine theta, 0, negative r sine theta, r cosine theta, 0, and then 0, 0, 1. So that would give us r cosine squared theta plus r sine theta squared. Yeah. And then that equals r cosine squared theta plus sine squared theta equals r. We know that r is greater than 0, so then the absolute value is also r. So then our last step dv. All right, so that's all they needed for that one. All right, now we're gonna do the spherical. Okay, so for the spherical coordinates, we know that we'll be doing the transformation P theta rho. From the Cartesian plane b theta rho to the Cartesian xyz plane. So then we also know that x is going to equal d sine theta. Nope, not theta, sorry. Rho cosine theta. Y is going to equal so then if we do the Jacobian, okay. All right, this gets wildly long, so we might need another slide. What are we on? 18? Oh, 17. Okay, we still, stop. All right, we still have some room on here, but I'm sensing we'll need some more. All right, so let's do the Jacobian first. We'll write it out since I now have an extra slide, so. I think I'm gonna draw that last one differently every single time. All right, that gives us okay. So if we're going to expand the determinant with respect to the third row, we're going to get this very ugly thing, which is why we're going to do it on a new slide. That had better not taken all my crap away. Whew. Thanks for the internet. Guys, about how to hide it. I would not have looked forward to having to rewrite all that. You wouldn't have needed to, and I wouldn't have needed to redo the video, but whew. Okay. Minus. This is the second to the last problem. So then that gets us minus. Okay. This is just crazy. We might need that last slide in addition to all this. Alright, so then that gives us minus. Oh my goodness, guys. Sorry. Ugh. I think even the tablet's done. It's like, this problem's long enough. I don't want to keep going. But it's still not done. These are one of those like crazy calc problems that like you hear about before you take calculus, or like your friends might ask you like, what's the longest problem you've ever worked on? It's not necessarily that the concepts are hard, but like that the hand cramp you get at the end of it is insane. So since, and unfortunately we still have the integral to squeeze in here, so we're probably still gonna need another slide. So I'm probably just going to put it there. All right, so since then we have to have so that means the Jacobian is going to be positive. Which tells us concentration is real with this one, guys. All right, it continues still, sorry. All right, that's finally it for that one. My goodness. We might not have enough room for the last problem. I might have to shorten it somehow. Okay, we'll see what we got. All right, so it says evaluating a triple integral with a change of variable, evaluate the triple integral XYZ space by using the transformation, then integrate over an appropriate region. So before some kind of sketch of region G in XYZ space over which we have to perform the integration can help identify the region D. So here's our figure that helps us do that. Clearly in G, the XYZ space is bounded by X equal to Y over 2. It shows you them. Okay. So using elementary algebra, we can find the corresponding surfaces for the region G and the limits of integration in a convenient list for these tables. So, all right. I'm gonna try and do this as small as humanly possible. Okay. So here's our list. We have equations in the XYZ for D. we're going to have corresponding equations in UVW region G. And then we're going to have the limits for the integration. All right, see if we can squeeze this stuff in. So x equals y over 2. So that would be u plus v, which is 2v over 2, which is just v, and the limit is u equal to 0. We also have x equal to y over 2, which is u plus v equal to 2v over 2 plus 1, which is v plus 1, which is u equal to 1. We have y equal to 0, 2v equals 0, v equals 0. We have y equal to 4, which is 2v equal to 4, which is v equal to 2. We have z equal to 0, which is 3w equal to 0, which is w equals 0. And then we have z equal to 3, 3w equal to 3, which is w equal to 1. All right, we use all of that. And now we're going to be able to find the Jacobian. I am not writing it all out because that's going to take up way too much of our room. So I'm going to do it very small. So we would have 1, 0, 0, 1, 2, 0, 0, 0, 3, which would give us 6. So the function to be integrated becomes f x, y, z, which is x plus z over 3. So u plus v plus 3w over 3, which is just u plus v plus w. So now we're ready to put everything in the problem. Oh, we might be able to get this. Maybe. Maybe. It's a hard maybe. If nothing else, I think what I'll do is I'll get you the beginning and I'll get you the last step, and you guys can probably find your way through it given what I'm going to give you. And if you absolutely need, I can send you an email of just this portion. Or a announcement or whatever you guys want, however you want it. But it might be a good way for you guys to work some of it out by yourselves. Okay, so I'll try to give you, I'll give you the next step and then towards the end, I'll give you the next step and then I'll give you the answer and you guys should be good from there. So it becomes 0 to 1, 0 to 2, 0 to 1. U plus V plus W, absolute value of the Jacobian, du, dv, TW, and your answer at the end is 24. So, again, if you guys need me to email that part, just let me know. I'm going to be working tomorrow. Stop the recording.